Today I'm going to talk about that S word, simulation, I'm afraid, but I'm not going to use lots of equations. I'm not going to use lots of equations because that's where I used to do, and I found everyone just fell asleep. But we didn't have any argument at the end, but everyone was asleep. But anyway, so I'm going to talk about the application of simulation to traffic design and dispatcher testing. And just to give a little bit of background, this was what I looked like when Gina was doing most of her work in simulation.
So what happened?
Yeah, I know, it's sad, isn't it? So that's some time ago, and obviously that's why I've learned an enormous amount from Gina. And this is what I looked like when I started working on simulation. My wife likes that picture of me. Anyway, that's so I've been doing simulation for a few years, and most of my time since then I've been doing simulation. So I have great fun and with simulation. I'm very grateful to the industry for supporting me by buying my product. Even though I'm a fan of simulation, I think it's absolutely wonderful. I totally agree with those people. Actually, most of the simulation experts in this room would agree that you should start with a round trip time calculation. Those good old-fashioned round trip time calculations. They're really robust, and we can talk about in CIBSE Guide D on section 4. I'll give you lots of bullet points if you want to go and read that. But it is a good practice. Even today, we're talking about simulation. I'm going to start with a round trip time calculation because it's actually very relevant. And the more I do with simulation and dispatching, the more I come back to the round trip time calculation and what we can learn from it. So it's an important thing. So let's just revise what a round trip time calculation is without looking at equations, because we don't like equations. So this is a lift at the ground floor at time 0, and a whole load of people get into the lift. And you get up, and someone gets out, and more people get out. It's very exciting, isn't it? It's better than paint drying, but okay. And then we've finished unloading people, and the car comes back down to the ground. And that was about 2 minutes in my example. And so in this instance, the round trip time was 120 seconds. And our whole model, traditional model, is based on that, just that single round trip of a lift. And there are some really exciting formulae, which we can talk about if you're interested in them, to work out the probable number of stops and the highest reversal floors and stuff like that. So if you're interested in those, you can look at the literature. So from the round trip time calculation, we estimate what will happen with more than one lift or elevator. And we assume that the elevators or lifts are equally spaced in time. So I should have changed this from elevator to lift because we're in the UK. I apologise, Gina. Okay, so this is my model of a round trip type, a perfect lift system. Okay, you see the red car, it's completely beautifully synchronised. Is this what Coney lifts do? No bunching at all, absolutely perfect. Okay, and so the round trip time with the red car was 120 seconds. Yeah, and as there were 4 cars, one was leaving every 30 seconds. And because of that, the interval is 30 seconds. So it's 30 seconds between the red car leaving, and I'll just run that just to prove it. Look, at 0 time, a car left, and then this second car left at 30, a minute, 90, and they are. So the interval is 30 seconds. And people tend to confuse interval and waiting time, but we heard about waiting time and quality of service yesterday, didn't we? So we'll move on from that. Okay, so we have a problem, and I don't have a good American accent, but that, if someone would like to say that out for me. Yeah, thank you, perfect. That's inspired by Bruce. Bruce Powell would have said that. I support a lot of people who use round trip time calculation as simulation, and what they do is they start with a round trip time calculation. They're really happy with it. They understand it. They even understand that equation, yeah. And then they change in the software, whatever software they use, from round trip time calculation to simulation, and they get different answers, and it's really frustrating. And Lufter, you said yesterday, wouldn't it be great if it all lined up? Well, Christmas has come. Okay. And if you go to Guide D in 2010, I did my best to explain how to line up round trip time calculation with simulation. And basically, in my training classes, what I do is I start with a round trip time calculation, and then I do simulation, and then it doesn't work, and I say, oh, well, this is why, and I go through these points, and basically we then end up simulating the round trip time calculation. Yeah, so we actually, all the things that we assumed in the round trip time calculation are slightly different to what we assumed in the simulation. But if you actually make the same assumptions in the simulation as you did in the round trip time calculation, it all lines up. And years of supporting people, I can say on my hand on my heart, it does work. Yeah, so you can line the two up. Now, it's sort of a cart before the horse now, and I spend a lot of time explaining it. And what I really want to do is go back into and correct the round trip time calculation. Well, correct it, but make sure people's round trip times assumptions are the same as their simulation assumptions. So we actually start. It would save so much confusion, and that's the direction I'm going in trying to encourage people to do that. So if you line it all up. And I didn't fiddle this result. It's extremely fluky, this particular one, but I got exactly the same interval for up-peak calculation simulation. All my inputs are in the written paper. I'm not going to show you them all. You can go and try them out yourself if you like. So it does work. It's not always that good, but it's pretty consistent. You can simulate a round-trip time calculation. Okay, so the average up-peak interval is 33.3, and in this example, again, I was very fortunate. It's not always this good, but it was about 60%. And if you go back to Strakosch, who we've mentioned 50 years ago, he said the waiting time is about 60% of the interval. Yeah, and it's and it's far more complicated than that. And I'm going to confuse you later with trying to discuss the relationship. But actually, at the point that what I call the design point, it's about 60%. And that's why when I design for an interval of 30 seconds, then I'm typically looking for about 20 seconds average waiting time. That's my approach. Obviously, we've got too much demand here, but I didn't use an iterative balanced method or enhanced up-peak. I used a regular up-peak. Okay. Now, when you move to simulation, and a lot of people, when they move to simulation, want to simulate a round-trip time calculation because they want the same answers. They want the same number of lifts, and that's fine. And we can do that. If you want to do that, we can do that. We have great arguments about how long and how wide the simulation is. And we on the forum a couple of days ago now, we were talking about whether when we do a constant traffic demand profile, which is basically saying we're going to have a constant level of traffic, should it be, well, some people say to me it should be 15 minutes, some people say it should be 30 minutes, and some people say it should be an hour. I don't really mind, to be honest. As long as we agree the same thing, we've got a benchmark. It's not real, it's just a system test. But actually, it's taken years, but I think we've probably agreed we're going to go for an hour, aren't we? As a standard system test, I think that's what we agreed. I was going to go for half an hour, and in my paper, I thought we'd come up with half an hour, so my simulations in the paper are based on half an hour. But people want to do an hour, so if you want to do an hour, we can do an hour. But we can line all things up. So what interesting happens, one of the reasons people get really confused is because the demand exceeds the handling capacity, and Lifter, you talked about that yesterday. If you took my perfect simulation of a round-trip time calculation, which is this one here, and then you actually put 15% rather than 14%, because the round-trip time calculation said I could manage 14%, but now I'm going to drive the simulation with 15%. Now there's more people arriving than can be taken away by the lifts. That's a bit of a nightmare, isn't it? So the waiting time goes up, and you can see we've got the waiting time, so that the interval stays around the same, in fact. The system's still working fine. System interval, lifts dispatching regularly, 30 seconds. There happened to be a big queue at the lobby, so the interval stays about the same, but the waiting time goes up. Now, if I run that was based on a half an hour simulation. So if we did a constant half an hour simulation, it went up to that. If I did an hour simulation, it would be longer because the queue would back up longer. And if you're interested in that, read Rory's PhD, because he did lots of long simulations and stuff like that. So that's great. And if you get to 16, the whole thing collapses. And you can look at this problem in many different ways. Carlo factors you'll talk about, I'm sure, Johanna. But basically, if you stimulate the simulation with more traffic than it can cope with, it'll collapse. Yeah, and we end up with something which I call, I think generally people understand as saturation. The demand is greater than the handling capacity. Okay, so if you want to avoid confusion with round-trip time calculations and simulations, you need to be consistent. Here the difficulties. You be consistent with door dwell times, and we can argue about what your door dwell time is, but as long as you're consistent with what you do in your simulation and what you do in your round-trip time calculation, we're okay. As long as you're consistent in the way you do your loading, car loading, with the way you do it in round-trip time calculations. And there's a slight confusion here because you can potentially get 9.3 people in a car in a round-trip time calculation, whereas you can't get 9.3 people in the car for a simulation. Yeah, so we've got this potential problem. But you can do that, and Gina taught me this one, you could just allow the car to load to 10, and then you can do lots and lots of simulations, and on average it comes to 9.3. So there can be consistency there. So you can achieve that. I'm afraid you're going to have, if you want to line up your round-trip time calculations and simulations, you're going to have to use a round-trip time inefficiency, and this is where Gina and I differ, because she's not trying to line the two up, whereas I am. So I have to do that if I'm going to line the two up. And for stability, so if I do all those top three, I'm good. I'm likely to get there. For stability of the system, for it not to collapse, I really need to just keep slightly away from saturation. I mean, my example was so close to saturation, it was perfect. If I just added another 10 people in my simulation, the whole thing would have collapsed. Yeah, but I was just at that saturation point. And because people go from round-trip time calculations and design at the saturation point, basically our maximum handling capacity, we're expecting the thing, we can just about get that 15%. Yeah? If you then give it 15.1, you're stuffed, or if you extend your door dwell times by a second, you're stuffed, the whole thing collapses. Yeah? So basically you end up with people simulating round-trip time calculations, but they've just gone over the edge and the whole thing collapses. And then they give me a call. And I spend all my time helping people understand the differences, and I'd really rather spend more time on the beach, really. So, so I want to make it simple for people. So constant profiles we talked about, a really useful system test. You can use different lengths, different widths, different heights. Another really useful test I found is what I call the step profile. You call it the stepwise profile. Different people have different names, but basically it's a ramp that goes up. This one in the current version of my software goes from one step to the next step, whereas I think the Otis one and the Coney one has a step, then stops, and the next step, and then stops. So there's different ways of doing it. But anyway, this is my one for what it's worth, and I found it really useful. And if I try to then compare my constant profile with my step, at the point at the 14%, which is what the handling capacity of the system was, then you can see again it lines up quite well. It would line up even better if my step was higher, was longer. Yeah, I've got a 5-minute step, so it doesn't line up that well. But if I had a longer step, the whole thing would stabilise. At the moment, I've got a transient thing because I've come from 5 minutes, going next 5 minutes, next 5 minutes. It goes up and down a bit. But I can pretty well get a consistency between the two. Now, that's all very interesting, and those are all system tests, and they're really useful. And if you want to use system tests, that's great. The background of the SIBSI modern office templates, well, I was trying to get people to agree how to do simulation. And I went to one lot of people and they said you should do it for 15 minutes with this profile. Another person said it should be 30 minutes and this one said it should be an hour. And I actually did spend several years before SIBSI Guide 2010 trying to bring people together with not a lot of success. And at the end I gave up and I said, well, if we can't agree, then, well, I'm just going to base it on what I've measured in the real world. And then we basically surveyed lots and lots of buildings, and we came up with a development of what, again, originally Gina's done with some templates, and then we built, this is my sort of worst case template in an office building. And it's in SIBSI, and you can see we've got some mixed traffic, or incoming, outgoing, and interfloor, because that reflects real buildings. And we got this lunchtime one here. And I'm, having used those since before 2010, I'm really quite happy with those now. I'm very comfortable I can get a sensible design with them. And again, Lufty was saying you want a systematic step-by-step. Well, actually, that's in Guide D. I know people don't read stuff if you write it down, but it is there if you want to do that. And it's for conventional control. Yeah, it basically will give you a good design. It will give you a consistent design with round-trip time calculations if you use conventional control. And the 5-star is what I'm aiming for, and I think we're going to drop that next time. We're just going to have not lots of stars, we're just going to have one target in the next edition of the guide. So you'll come up, if you go through the design procedure, you should come up with a pretty similar answer if you're using this or round-trip time calculations. Now, there are loads of things we discuss here, and we just touched on them in a day forum a couple of days ago, and this is slide 39. So if you have time at the end and we want to debate some of these things, we can come back to slide 39. You remember that one? And there's about 60 slides, so how are we doing? Not too bad. Okay. Now I want to talk about the relationship between interval and waiting time, because that's something that confused me for years, and I think I've got the hang of it now. So this is an ideal relationship. So you've got a person arrives at 0 seconds and they just missed the lift. Okay, and this person arrives at 30 seconds, there's a 30 seconds interval, this system, and they just catch the lift. Okay, so there's lots of people, if they don't follow a Poisson process, but they just arrive equidistant in time, and you get the average person in the middle there. So in an ideal system, if you've got an interval of 30 seconds, you should end up with an average waiting time of 15 seconds. Of course, we know things aren't ideal, again, Gina did a whole lot of work. It's actually a function of loading this relationship. Strakosch said 60%, and actually about the design point, it tends to be about that. But anyway, that's a simplified demonstration of it. Now, I find this the best way to understand this relationship between interval and waiting time is to drive the simulation with a step profile. So this is my step that I'm driving the system with, and this is the plot of interval as the demand increases. It's sort of not a linear relationship, and so Strakosch saying it's 60% between. Sorry, this is the waiting time. So we were talking yesterday about sort of trying to get formally to describe the relationship between this one and this one. It's not really very linear. It's okay around the design point, but other than that, it's quite complicated. So let's have a look at the individual characteristics and what's happening where. At the beginning, when you've got hardly any traffic, most of the lifts are just doing nothing. Yeah, so there's nothing happening, and therefore, if you define interval as the time between departures from the main terminal floor, yeah, then actually, if there's no traffic, the interval becomes infinite. Yeah, there's no traffic. So we've got a high interval because nothing's happening. Now, as we go up, as in demand, we find that the interval, we have a low interval because the cars are cycling, but they haven't got many stops. Yeah, so the round trip time is quick. They come down, and then it comes up to this point where it gets to about the 30 seconds, which is what we're expecting from the round-trip time calculation, and it stabilizes. And it stabilizes because the system is working really well. It's dispatching a car every 30 seconds. But as we go up in demand, we end up with a big queue. So as the longer we run the simulation, the longer the queue becomes, the longer the waiting times become. Now, at the end of the simulation, we get this funny anomaly here, where basically you're just serving the last couple of passengers. So again, a lot of the lifts are just stationary. Yeah. And Gina, I have lots of debates about what you should present on this, and she would probably say chop off this end here, not to confuse people. Yeah. And possibly this bit there, and only look at this bit. And we could do that, but people just to understand what goes on, that's what's happening. Now, this is up peak traffic, by the way. So this is what happens on the waiting time. So right at the beginning of the simulation, you see you've got no waiting time because there's always a car there with the doors open. So the red line is the waiting time. This is time to destination, but we'll look at the waiting time. So here, up to this point, there's always a car there ready for you. And then they start cycling. There isn't always a car for you. And then at the sort of 14% demand level, it all works beautifully, and it's a 60% relationship, and everything is good with the world. And then we end up with more traffic, and then the queues get longer and longer, and people have to wait more and more intervals until they can get into the car, and then the whole thing saturates and falls over. And that's why in all the guidance where you extrapolate waiting time from interval, it says check it with simulation. It's complicated. If you can get a reliable equation to do this relationship, then that's brilliant. I'm looking forward to it, but I haven't found one yet, and therefore if I'm going to check it with simulation, I'll start with simulation. It's easier. So there are some other difficulties with interval. Non-peak traffic, and I'll refer to Coney. You've got some good things with non-peak traffic with round-trip time calculations, really interesting. But again, because I do simulation, I don't worry about that and just go straight to simulation. Multiple entrance floors, that can be complicated with round-trip time calculations, because if you've got 6 entrance floors and you define interval as the time between departures to the main terminal floor, well, actually sometimes you go past the main terminal floor. There's a good paper from Dr. Powell, Bruce Powell, about that, multiple entrance floors, some issues there. And then you get destination control. And when destination control was first sold, people still reported the interval, but actually you didn't get into the next car to depart. So the interval was actually a meaningless measure of quality of service from in the context of destination control. So interval is a great measure, and it's a great measure in a round-trip time calculation. But when you start using it in simulation, it starts to get really confusing, which is why I encourage people when they move to simulation to start thinking about waiting time and time to destination and all these other parameters. Now, I thought I'd put this in because I think this next slide I think is the most interesting slide, and if you're not interested in dispatching design, you can turn off for a couple of seconds as I talk about this one. But this one is, the dotted blue line is passenger demand. So this is my step profile. And it's just increasing, and it's increasing to the point that the system saturates. And the red line is what I call the passenger demand. So that's me and Elizabeth counting people in buildings. Yeah, that's actually the number of people that actually get into the lift, and that's one of the graphs that we produce. And you can see as the demand goes up, and you remember my handling capacity was 14%, and if you watch the red line, that actually it separates from the demand curve at 14%. Yeah, and that system, that red line, it shows you what the handling capacity is, and this is a really good way of working out what the handling capacity is using simulation. Quick one shot, you know the answer. So I find that really interesting. Now the green line is even more interesting because that's destination control. And of course you'd expect because you get extra handling capacity, this is in pure up peak with destination control, you'd expect to obviously to get for it to depart from the line later. So this one goes up, and although this one collapses, well, it doesn't. We start having queues with conventional control at 14%. We get up to about 18%, and we're still on the line. So it's great, and it is true. And if you go into buildings, and I've been in buildings where destination control has been turned on, and the day before it was turned on, there was a big queue in the lobby because it's saturated. Conventional system is saturated. The day the destination control was turned on, there was no queue in the lobby. Well, no, it was clearing, and you actually do get extra handling capacity. It's real, believe me. But what people think is this is so brilliant. We can put less lifts in, and then they get to the point where destination control saturates, and that's a disaster. I mean, not just the ones I've worked on. I've seen destination control saturate in real buildings, not just in simulation, in sort of in probably about 5 different implementations of destination control, and then it really is a problem. And there are ways you can fix it, by the way, and I think that's there's a pattern that Roy and I have got, but there are lots of different ways you can fix it. But you can see this collapsed, yeah, and we got down to 10%. Yeah, so the handling capacity was reduced. So that's a big warning for people who are going to put less lifts in because they're using destination control. Don't go too close to saturation. Yeah, we might have a problem. Okay, So dispatcher testing, obviously, what the step profile does for me is it allows me to test the system across a range of traffic intensities. It might be that the system works great in 100% up peak at 13%, but it might not work very well at 7%, which is actually more likely where we're likely to get. And it might not work very well, and there are very strange occasions when we get 15 or 16%, and the whole thing might collapse. So what the step profile does is allows me to say, okay, test this system across a range of traffic intensities, and then I'm looking at different mixes as well. A lot of people like to do up peak because that's the traditional way we did up peak calculations, but it's really interesting to look at down peak, and it's look at mixed a mixture at lunchtime and so on. So you can do all that with the step profile. And you can you need to do other things like look at how the dispatcher deals with multiple entrance flaws. And if you do all of that, and your system works with all those step profiles, I can test, and all the dispatcher designers, it's lovely to have you all here, I can test it'll work really well with the SIBSI profiles. Yeah, that's my thesis. So it's a good preparation. I need to wrap up quickly. Yeah? Oh gosh, I've gone on, haven't I? So dispatcher bake-offs, it's actually less than 60 slides. I was exceeding expectations. These things that Hansi Apson and co do, I can design to that if you want to. If that's how you want to compete on dispatchers, I'll design dispatchers to these tests. But to conclude, I'm a musician, yeah, and I'm a musician, and I think actually it's a good analogy with traffic calculation. So the soprano recorder is the first one I learned. It's a bit like the up-peak calculation, and the alto one is like the enhanced up-peak calculation or iterative balance method, or your Harry Plane type thing. I can't remember what it was called. And then you've got the general analysis here, which does mixed traffic and a round-trip time calculation. And then if I was going to do more work on round-trip time calculations, I'd go and talk to you about the Monte Carlo method and apply it to general analysis, and we might remove the idle times like you do, and it'd be something like that. So that's it is. No, it's not. You see, it's great, and it makes a lovely sound, and I love the recorder. But I like the piano better. And the piano is my simulation. This actually is the piano is my simulation, and this is the one I'm working on. There's some more here. This was my first simulation, and some people are still using simulations like this. So this is sort of where I'm at the moment, really. You can play. You just get so much more richness you can play with. You can do so much more and learn so much more. And a lot of people buy my simulation and they play it with one finger because they learn the recorder and they know how to do the recorder. But and if you want to spend lots of money on simulation and play with one finger, that's fine with me. It's good. I don't mind. But I'm gonna play the full score. So that's it.